Hello everyone, my name is Christine Park and this is Lab 4 Oscillations. So just for a brief introduction about what I did in this lab. So the objective of this lab was to compare observed and predict the motion of an oscillating object. In this case, it was an object suspended by a rope and then released at a certain point. So I'll analyze the video of this moving object and track its point mass between different frames to find X and Y position data at different times. I'll then use these data points later to create a CSV file to compare and input into the computer model. Then I will also use values from the video data to find values for the spring constant, and L0 to input into the code. And then I will finally compare these data sets and create a computer-generated model to find the changes in energy, including kinetic energy, gravitational potential energy, spring potential energy, and total energy, as well as position data. So the principles that were addressed in this lab are the momentum principle, energy principle, and Hooke's law. And according to the energy principle, the change in total energy is equal to the change in kinetic energy plus the change in the potential energy of the spring plus the potential energy of gravity, where the kinetic energy is equal to 1/2 mv squared, potential energy of the spring is equal to 1/2 the spring constant times s squared, and the potential energy of gravity is equal to mgh. So in this case, what this means is that if there are no other energies introduced into the system, the change in total energy is equal to 0, meaning that the energy is conserved and that the system is closed. So I'll show you my tracker data now. And this is what my tracker data looked like here. I then took the X and Y values and put them into a spreadsheet program to generate a CSV file that I later put into the code. So now I'll go into how I found the spring constant. So I used the period of oscillation formula, which is T equals 2 pi over W, and reworked it together. The spring constant is equal to 6.341 newtons. And then for finding L0, I used the formula Fg is equal to Fs, put in my known variables, including the spring constant, and got that L0 is equal to 0.1227. So in the code, I updated the mass to 0.402. Then I updated updated G, updated the spring constant, updated L0, and then I updated these following statements to compute the initial energies. And then I'll go into the loop calculations, where I rewrote statements to update the force of gravity at different points as well as the spring force at different points. And then I created a statement that says that the net force is equal to the force of gravity plus the force of spring. And the following statements will update velocity and position as the object is oscillating. Moving forward, this statement, 1/2 the ball's mass times the magnitude of ball velocity squared. So these following statements account for the change of energy over time at different points, and then the following statement just designates colors to the different energies. So as you can see here, these are my observations, where red is equal to the change in potential energy of the spring, green is equal to the change in potential energy of gravity, blue is the change in kinetic energy, and yellow is equal to change in energy. As you can see here, the yellow line is equal to 0, meaning that the total change in kinetic energy is equal to 0. So for change of position, you can see how the data sets are similar, the red being the observed motion and the blue being the predicted motion. However, you can see that the predicted motion is slightly overprojected or overestimated, and this can be attributed to the fact that we did not account for forces like drag, and then also there could be some human error when it came to plotting the point mass of the object in the tracker software. So to answer question 1, is the energy principle satisfied? As you can see here, the energy principle states that the change in energy is equal to delta Ke plus delta Us plus delta Ug. And as you can see, with the yellow line, which equals delta E, it is 0, which means that it is correct. And to answer the second question with the periods of oscillation in the X and Y direction to compare them, I used the tracker software and found the distance between the peaks. So for the X direction is 1.58, and for the Y direction is 1.472. In a perfect world, in theory, these oscillation periods should be identical. However, we can see that they are similar but different, and this can once again be attributed to unaccounted drag force as well as human error when it came to plotting the point mass of the object between frames.